Hello everyone, Prashant here. In this module, I will try to explain the MATLAB based experiments on realizing various types of filters. The filters can be IR filter or FIR filter, and based on the type of specifications, you can design maybe a low pass filter or a high pass filter or a band pass or a band reject filter. Okay, for that I'm trying to explain this using the Simulink library. So on your MATLAB command window, or in the command screen, you can open the Simulink block by clicking on this particular icon over here. So if you were to click on this, you will get a variety of libraries that you can see. Okay, so computer vision system, for example, embedded coder, for example, control system toolbox, maybe you are aware of it. So image acquisition toolbox. So many tools are available. In this, as I said, we will be working on DSP system toolbox. Okay, in libraries you have a DSP system toolbox. In that there are varieties of operations available. I'm going to use the block called filtering block, and in this there will be filter implementation block. So first what I'll do is I'll take a new um, file over here. So in this also you get the same Simulink library browser, so you can keep it this way, and take the required toolbox from here, drag and drop it over here. As I said, DSP system toolbox, in that filtering, in that filter implementation. If you double click on the filter implementation, you get to see a lot of blocks over here. I'm interested in this digital filter design. So you can click on it, drag and drop it in your file that you have created. Okay, so this is the box now. So if you double click on this, a dialog box opens with if you were to enlarge, you will see varieties of options over here. Okay, so so let's look at each of them quickly. So here it is, this particular portion is to select which type of filter you want, whether low pass or a high pass or a band stop or a band pass filter. So you can click on that. Then design method, basically you have IIR and FIR, so radio buttons are there. So I want just to demonstrate the Butterworth filter now, so you can click on this one, IIR filter, Butterworth. And then over here you have the filter order. So it's a low pass Butterworth filter. The order can be, you can specify the order over here. For example, if the question is to, or if the requirement is to design a third order Butterworth filter, then you can write it as 3, or that is one possibility. Or if you want to give the order, then obviously you need to click on this, which will open up other possibilities, like it will ask the attenuation in the pass band and stop band and such other details. Okay, so this I'm selecting the minimum order. So you know the formula for this, half into log of 10 raised to zero point 0.1 as minus 1 by 10 raised to zero point 0.1 ab minus 1 by log of omega s by omega p. Okay, so that formula will be used by the software, and it will decide the minimum order. Okay, and over here the frequencies will have to be specified. So one is this normalized to 0 to 1, and the other one is this in terms of hertz. Okay, so see that this particular frequency specification is based on the type of value that you are going to specify. So it is possible that the specifications are mainly based on mainly based on the sampling frequency. Suppose if you are giving a frequency of say 10 hertz, and over here maybe 20 hertz example. In that case, you ensure that it is at least 2 or 3 times more than that. Okay. Over here, let us take one example. I'm going to consider a frequency of, say, example 25 hertz over here. Okay, that is the pass band edge frequency, and the stop band edge frequency, let us consider 50 hertz. So 25 hertz is the pass band, 50 hertz is the stop band. So in this case, I'll make it say something like 2000 example. 200 would have been also sufficient. So it is unities in hertz. And attenuation in pass band, let us take it as say 2, and attenuation in stop band, let it be say 15. Okay, example. So just all these informations are to be given, and on the right side corner bottom you have this design filter. So you click on design filter, your filter is ready. Okay, so you see here on the current filter information is on the left topmost portion. So it is a third order filter, and the filter response is going to be like this. Okay, so since it is given till 2000, I have it is dragging on till here. So maybe you can make it as say 500. Okay, 500. If you make it, then we'll redesign it. Okay, yeah, this looks good. So it is our pass band, and gradually the attenuation is increasing, and the response is given all the way till at least half of the sampling frequency that you have given till 500, so it is showing the result till 250. Okay, so this is the magnitude response. Now you have to observe various parameters can be evaluated. I'll just click on this thing called filter information. You will see that the it is going to be the type of filter that has been designed is having these specifications. So let us see here. Okay, yeah. So design specifications, it's a low pass filter. Pass band and stop band edge frequencies are like this. Attenuation given this way, and all these 3 decibel point and 6 decibel point are also given. Okay, so this is how. Now let us take the waveform again. So this magnitude plot is like this. Maybe let us click on this icon here. That is this particular icon, which gives us the possibility of full view analysis. So if I were to say enlarge this, I'll get this whole wave plot of magnitude of that versus the frequency. On this, you can click anywhere. Okay, the waveform, it will show the various frequency values, and correspondingly what is the attenuation or gain that is happening. Okay, so let's just drag it over here. You can see the 3 decibel. Okay, point is somewhere over here. Okay, I'm trying to adjust that. So it is a 29 hertz. Okay, so this is actually the cutoff frequency. Okay, this is the response of the filter is going to be around -3 decibels at the cutoff frequency. So if you remember, what were the parameters for the frequency cutoff, pass band edge frequency was 25 hertz, and stop band edge frequency was 50 hertz. Okay, so you can see that the this is how the response is. Okay, now suppose if I want to instead of the order being calculated this way, if I were to make it a little higher order on my own, say for example eighth order filter, and cutoff frequency, let us have the same way as I think 25 hertz or so. Okay, and sampling frequency, let me make it as a 250 hertz. Then cutoff frequency, the moment you give the order, that is the order should be 8 or 10 or so, then there is no requirement of attenuations in the pass band and stop band. So this attenuation at cutoff frequency is going to be fixed as 3 decibel. So with that itself the design will be done. Okay, now you can see the specifications are like this. Now instead of 8, if I were to design an 80th order filter, then obviously the cutoff frequency is going to be very sharp, and it is, and rest all other frequencies, the response is monotonically decreasing. So this is how our filter. So this is the cutoff frequency. You can see I have given cutoff frequency of 25 hertz. So somewhere around uh, up to say 24 25 hertz, the magnitude has fallen down to -3. But up to that value, very this gain is exactly being same. It is not altering. Only after the cutoff frequency the attenuation is increasing. Okay, this is how the waveform can be. Then if you want to see the, instead of Butterworth filter, say for example Chebyshev type 2 filter. Okay, so again let us consider cutoff yeah. So this way, you also have the other options, like already the waveform, that is magnitude response, has been already shown. Let's only take this x-axis. Let us zoom the x-axis. Okay, so keeping you can see how the ripples are there in the stop band. Okay, this happens to be the stop band, and you see the ripples in the stop band. This is a Chebyshev filter type 2. Let us make it type 1. Okay, same specifications. You can see there is this no, I will make it say 960 hertz example maybe, and design filter type. Yeah, so attenuation in passband. Now you can see it is type 1, and if I were to um, let's redesign this. I will change the parameters here to say 500, and I'll try to redesign this, and you can see. Let us now use this zoom y-axis option and see if there are any uh, uh, oscillations happening, ripples happening in the yeah. So you can see how beautifully this waveform is showing the ripples in the pass band, because I have chosen Chebyshev type 1 filter. Okay, so this is how you can feed the values into the this dialog box, and it will give you the response, magnitude response, and phase response. But what about the filter coefficients? If you want to use the filter coefficients, you can't just see the waveform, no? So you will require actually. So filter coefficients can be, you can obtain the filter coefficients if you click on this one. So it will show you the numerator, the denominator, and the gain, and so on. Okay, this is giving you section by section, because there are 80 or 80th order I have taken. Okay, and let us say reduce it to say for example maybe say only third order filter. So if it is only third order filter for this particular specification, designing filter, it's already done. So you see denominator, it is having these coefficients, and there are only two sections over here. Okay, each section is going to be second order. So this is how the filter coefficients can be obtained. Okay, filter information. Again, as I told you, it is giving you all the specifications of the filter. And the phase response is also there. Yeah, this is phase response. Then I want to again show you, maybe you can overlap both the magnitude as well as the phase response over here. One more thing is this pole zero plots over here. Okay, so the plots are also shown. If you know on the left hand side, this particular this um, side, left hand side, you see the various options. There are some 3 4 options, so let us even see further thing also. Each section will have a particular pole, so this is shown. Then I want to show you the realizing this model, because the last experiment is about the realization of the filter. So realizing the model is, if you click on this, you will see various options. So in this, I want you to click on this build model using basic elements. So obviously basic elements are our delay elements and gains on the gains. So if you click on that realize model, you will get this thing. Double click on that, you will see a very nice realization of the filter. So you can see that this is a second order. We had designed a third order filter. Okay, so there are 2 sections now. Each section is optimized for second order. So it is a cascade connection of individual stages. So that is also one type of realization. I shall show you in the further classes. So this is a cascade arrangement where this is second order, and this is a first order filter. So first order filter in series with the cascaded with this first order filter. So 2 and 1, you will get third order filters. Okay, so this is how you will realize the filters. Yeah, and okay, so these are some of the discussions that you could do, and let us also further maybe see the um, other types of filter also. High pass, if you want high pass, you'll have to just click on this. Then correspondingly the parameters get changed over here. It can be one of these things. Okay, so any one such options can be used, and you can give the data into this particular module, and then you can ask the design filter. Now once the filter is ready, that filter will have to be used, wherein input signal is given to that filter and you can observe the output. Okay, so that and other things we can discuss further. Okay, if there are any doubts in this, you can always text me. um, uh, you know we'll meet with the further discussions in the next video.